today's presentation and webinar is really around how we can reimagine deep learning networks. As we go through this, there are few key ideas we have been working on, and we have been in existence for about a year, and this is practically the culmination of 1 year of work we have done. ThirdAI was started April of 2021, so we are almost a year in. Today, we are about a team of 12 engineers. I'm the head of engineering. Tarun is the CTO, and Anshu is our CEO. I come from about multiple companies in the past. I spent last 6-7 years at Amazon and AWS working on multiple ML problems. Tarun did his PhD from Rice. He also spent time working at Amazon Search and Target in the past in recommendation engines. Anshu is an associate professor at Rice University, and he has been primarily focused on using data retrieval techniques to make deep learning networks better, neural networks in general faster. Our investors are NeoTribe and Servin Ventures. They gave us the seed funding and helped us build all of these. A lot of work we have been doing so far is based on about 8+ years of research on large-scale machine learning using information retrieval techniques. We will go a little bit more deeper into how information retrieval helps us in building better networks, but they are all tightly interrelated fields. In fact, if I look at the list of attendees, a lot of folks come from NLP background, and I think you will appreciate how all of these areas intersect with each other. Our team has successfully implemented multiple of these techniques at several large companies, either as interns or as research scholars at several large companies, including Amazon and Google. One of the key insights we had is that these techniques seems to be much more widely applicable, and we want to find a way to bring it into the market, and hence ThirdAI. Right? So let's quickly step back and look at what deep learning means, right? Deep learning has been a huge, huge success. We have multiple advances in the last 15 years. Irrespective of what field we do, today when you talk about machine learning, it has almost become synonymous by using deep learning networks. And it has been multimodal, right? You can work with audios or like Siri, Alexa, and other things. You can recognize words and sentences and commands using deep learning network. We have made tremendous progress in images, image recognition with deep learning network, object segmentation, image recognition, object detection. Self-driving cars today use deep learning network. And interestingly, drones use deep learning network to navigate through obstacles. Natural language processing has been in deep learning. But one of the key insights we have realized is that all the progress has been made because, or rather a lot of progress has been made because we have learned how to model problems as supervised learning problems. Natural language is a great example. One of the questions has always been, how do you make machines understand semantic meaning, semantic structure? Huge progress was made when we realized we could model the problem as a supervised learning problem. We have masked language models, next sentence prediction, sentence order prediction. They all convert unstructured data into a supervised learning problem, and we can train deep learning networks for it. And for folks who are very new to it, a quick recap of how it works, right? Let's say I have the sentence, I love chocolates. The way our network works is that it takes the sentence, it breaks it down into words in general, and each word is represented by a number. The network uses these numeric representation and predicts an output. We compare the expected output with the predicted output, and depending on the difference, we readjust the weights in the network back, right? All of us know how this works, and this is backpropagation. The reason supervised learning has done so well is because the backpropagation is the key, and we have I can't re-emphasize how much it has improved, right? Starting from 2003 or so till now, we have made improvements not just in modeling the problems, but also in optimizing and running these networks at large scale. There are few things we know about deep learning after using it for such a long time. The first one really is that bigger the network it is, the better it is, right? Here is a graph on the left. These are popular NLP, natural language processing models: GPT, BERT, GPT-2, Robota, GPT-3. On the left, you see the model in a linear scale, and on the right is on the logarithmic scale. But if you look at it, the number of parameters in the model has just shot up. We are talking about GPT-4, which is about 10 to 100 times bigger than GPT-3. We do know that larger the model it is, the more parameters it can learn more complex things. The second thing we learned is that larger models need a lot of data, right? Here is the data set size in GB, gigabytes. When we start with GPT, it is about 16 GB. GPT-2 increased it to 45 gigabytes. GPT-3 just took it to about 40 terabytes. And now we are talking about even more larger data. The reason large models need large data is because you have so many weights that you want to adjust. And without that amount of data, you end up with not great prediction. The third one we realize is that longer training yields better results. This has been a very interesting thing because there was a very popular anecdote where Andrej Karpathy, working on Tesla, he has been trying, he accidentally left a model running over the winter vacation. And when he came back, it achieved state-of-the-art score. We do know that if you train it longer, it does tend to optimize better, and it yields better results. The fourth one, which is more a practical point, is that models also need to be constantly retrained. When working at Amazon, for example, we will train the recommendation models every night over and over again. The fact is that reality drifts away from what we have modeled, or model drifts away from reality, whichever way you prefer. And when people use the model, their interactions change. So it is a very nonlinear relationship, and we constantly have to retrain the model to match what the real data shows us. And the last one is pretty interesting too, because we realize that the model weights can be approximate. We don't really need the highest precision possible to get good results. In fact, the last one itself has started an entire subgenre of model training, deep learning, which is about quantizing models and distilling models. Since we realize that model weights don't have to be accurate, for example, we can train model with 32-bit precision, and then we can quantize it, reduce the size of it using int8s. And with a very small loss in accuracy, the model seems to perform exactly as well as you would do if you are using high precision computation. We also do dropouts of layers and other things to reduce the model size. But the fact is, model weights can be approximate. We don't have to necessarily have very, very accurate computations in there. Given all of these things, we also know we have few limitations with deep learning today. The first one, and probably the one everybody is familiar with, is that the backpropagation is computationally very, very expensive, right? So the way we think about it is that if you have 1 million parameter models or 1 billion parameter model, every single training sample goes through the forward pass. We compute the prediction. We compute what is the difference between expected output and this. Then we walk back, do the backpropagation calculations. Every single weight of the billion parameter model has to be updated. We don't update it all the time, but the computation still has to happen. And we constantly keep these large matrix computations constantly running. The second one is memory constraints on large data sets and model are playing a huge limiting role. In today's world, to do these matrix computations really well, we end up using GPUs. But GPUs are limited in memory. If you have a, we have some techniques of data parallel and model parallel, but they all end up being they all come with their own problem. So we have limitations in terms of large data set and large model, and we seem to be kind of hitting the limit on how much we can we can take it forward. The third one is we talked about quantizing the model because weights can be approximate, but we also realized that once you quantize it, they seem to lose their learning capability. You can't take the quantized model and retrain it. We know models has to be constantly retrained, but retraining doesn't seem to work very well after you quantize it. So we end up keeping two models all the time. One is the model with all the weights and 32-bit accuracy. The other one is the quantized model that we use for inference. And we walk back and forth. We train the big model every night, quantize it, run it for inference, then train the big model every night, quantize it, run for inference. And this cycle creates a little bit of a issue in some ways, that the model you are running for inference is not really the model you trained. The last part we spoke about being GPU dependent for model training. This kind of dedicated hardware creates friction. It has been one of the big challenges really, that GPUs are expensive. They're also hard to get. Today, if you want to go to AWS, for example, and try to get a GPU, it's not that easy to get one. It takes time to get those GPUs. It takes even more time to set it up as part of your pipeline. Large companies can do it, but for most people, actually getting this up and running itself is a pretty hard task. And this is really our current state of union on deep learning. Tremendous progress, a lot of problems have been solved, but it comes with its own challenges. So there has to be a better way. There is a better way. You remember when we talked about backpropagation, how all these weights have to be readjusted back for every training sample, right? The interesting thing is that when we actually run through this, you will see it in examples, but the first few epochs, first few runs of training actually trains the model to a fairly good extent. You are going to see it in the example from Jordi, for example, that your first epoch actually gets to about 85% accuracy. And every single epoch after that will train it for a tiny bit more. What happens in reality, if you notice the weights and how the weights get adjusted in this case, is that most of the changes to the weights end up being trivial. There are only few weights that change in significant ways for a given sample. If you could find out which weights need to change for a given sample, then we only need to compute those, because remember, the weights can be approximate. So if a weight changes by 0.001, we could as well ignore those change. So that is one of the key insights we had, and we will talk a little bit more about it as we go through this. The second one, which I also want to call out, is that CPU is still dominant in ML and AI. As much as we talk about how NVIDIA cores are doing really, really good, a lot of hardware usage for ML and AI is still on CPUs. Our inferences, we run it pretty much on CPUs. GPUs become very expensive to run inferences on. While for training large models, GPU is still the king. CPU is the primary processor. So if we could have a method, if we could have a technology that could take these ideas of approximate weights, idea that not every weight is equally important, and run it on CPU, we would have an awesome solution. ThirdAI is the only company that accelerates AI training on CPU with sparsity. Sparsity talks about how well you could select weights so that you don't have to update everything. And we could do really, really large optimizations and acceleration on AI training and inference on CPUs. I want to dive a little bit deeper into what does sparse computations really mean. This is from a presentation from Jeff Dean. He gave this talk about a year ago, July 2021. But the idea behind it is that given an input at every layer of the network, we don't have to train all the weights. Select the weights that are the most important one, train only those, and that would lead to our output, right? So that means that for every input, we keep selecting only a subset of weights. Even though the model can be a billion parameter model, the actual computations will be only in few thousands for a given input. And back propagation works the same way. You only need to recompute it for the few thousand. So in some ways, you could think of a sparse model as multiple overlapping small networks, all getting trained at the same time. And each network trains for a set of input parameters. This idea of, we kind of do it in some ways with other techniques like mixture of experts, but mixture of experts is really multiple non-overlapping small network, whereas here we have got overlapping network. That means that there is cross-learning between inputs, but it is, the computations are a lot smaller, a lot less than what we do. Sometimes we ask the question, it is worthwhile asking the question saying, how much better can sparse computation be to dense computation? Because we have got all of these techniques and hardware acceleration for matrix multiplication already built into GPUs. Is sparse really going to help that much? And here is a good example of how much better sparse computations can be, right? This is trained on a data set called Amazon 670K. The goal of the data set is to predict or recommend one of the 670,000 products given a user query. A reasonably good score on the product is somewhere around 35%. If you can predict the one product out of 670,000 products with 35% accuracy, it's considered pretty good. So on our CPU machine with Bolt engine, you see the green line. We hit pretty much the state-of-art accuracy in about 2,000 to 3,000 seconds. The exact same network trained with a GPU on A100 reaches the same accuracy in about 7,000 seconds. So we are getting about 3 times the speed up right here against a GPU. With a CPU, it ran for a much longer time. It did not even come close to it. So that is the kind of difference you can see if you optimize on the computations. The primary thing that neural networks do, deep learning networks do, is constant computation, and every single change in there leads to massive benefits. The graph on the right also talks about what is the time per epoch. And you could train the same deep learning network on a laptop, for example. We trained it on AMD, Intel, Apple M1 laptop. It's the exact same code, and you can see the time per epoch. It's amazing how much reduction in computations can lead to. What we found was that we could get up to 50x acceleration for both training and inference on CPUs using sparsity and smart computations. Our core tech is around these ideas, these key ideas. The first one is really that we have a set of technology and set of algorithms for smart hashing. It tells you how to pick up which neurons should we train for a given input. And how do you reduce the number of neurons to train, both for forward pass and backward pass? The second part of our engine is Bolt, which is a sparse deep learning framework. It does both sparse and dense computations, but it is really, really optimized for sparse deep learning on CPUs. And the third one is MaxFlash, which is a hyperdimensional vector search. A lot of times we end up solving needle in a haystack problem. Given a large number of vectors, find the one vector that is closest to our query or the one we are looking at. And MaxFlash solves the problem very elegantly. Both MaxFlash and Bolt use a smart hashing as a way to use information retrieval ideas to solve deep learning problem. And you would actually see a demo of both of these. Jordi is going to show a demo of Bolt, and Josh is going to show the demo of MaxFlash and what it can do. So while you are looking at the demo, keep an eye out essentially for both the speedups in the training and the speed up in the inference. Right? Our core capabilities that we do want to demonstrate is really that we can accelerate AI training and inference on CPUs. And our code works with any CPU. It can work with Intel, it can work with AMD, it can work with ARM, and it is the exact same code. We don't have, it's not like 3 different branches that we are doing. We have proven demonstration of over 50x speedup, especially with sparse inference at large models, since your computations are 50x less than what you do with a large model, you get the speed up. And the last part is that the engine is designed to have acceleration by design. What it means is that if you define the network in Bolt engine, you would get the acceleration out of the box. You don't have to do anything different, right? So it's easy to talk a lot about it, but a lot of times actions prove it much better than words. So I would like to actually invite Jordi and Josh to give a quick demo of what you have built so far. As you folks look through the demo, please keep an eye out for specifically on how we define the network, how we define the sparsity in training and inference, and the speedups you would get by looking at sparse inference and sparse training. Jordi, over to you.
Hello, everyone. Thank you so much for coming to this webinar. My name is Jordi. I'm so excited to be here today to show you how to use Bolt, how you can train really fast with Bolt, even if you have really large networks, the benefits of large sparse models, and also demonstrate how fast we can do inference. To start off, we want to show you how to actually define a network in Bolt. And to do that, we're going to do it with a simple exercise. We're going to do image classification with MNIST. So this data set consists of images that are 28 by 20 pixels in size, and they're images of handwritings of numbers between 0 through 9. And the network is supposed to learn to predict what number is actually written in there. To do this, we're going to use a very simple neural network. We're going to have a 784 dimensional input, that's 28 by 28, followed by a 1000 dimensional hidden layer with ReLU, and also a 10 dimensional output layer with softmax, so that we can choose between 0 and 9. And in the first cell here, you can see how you would define a network like this in Keras. And in the second cell, you can see how you can define the same network with Bolt. We put a lot of effort into trying to make this as familiar and approachable as possible. So as you can see, the syntax is very similar with popular deep learning frameworks. So it should be very easy to transition into Bolt. Now that we have defined our network, we can now train it. We're going to train it with categorical cross-entropy loss, because this is a classification task, and we're going to predict with categorical accuracy. That is just how many of the predictions we got correct. And as you can see, we just trained our first network, and we got around 95% accuracy, which is great. We now trained our first Bolt network, but that's not too special, right? Like, you can do this with any deep learning framework. And this is kind of like the hello world task of deep learning. So instead, here we like bigger models, and because bigger models allow us to do more complex tasks. And one such example of a more complicated task is intent classification. Here we're going to demonstrate that with the Clink 150 dataset. Now, this data set consists of customer queries. So for example, things like, oh, do I have to pay for carry-on on Delta, right? And then it maps these queries to the IDs of the intentions. So for example, the query that I said before, maybe the intention is carry-ons, and carry-ons might have an ID 42 or whatever between 0 and 150. And so the task here is to predict, given a query to predict what the unique ID of the intention is. Now, in this case, as you can see here through the input dimension parameter, we have vectorized the queries into vectors of around 5,000 dimensions. And after that, we're going to pass it to a hidden layer of 10,000 dimensions. And finally, onto the final layer, which is 151 dimensions. And if you do the math here, it's a 51 million parameter model, which is pretty big. If you compare this with other deep learning frameworks, it would take about 100 seconds to train each epoch. But here we have a special offering here, which is load factor. Now, if you take a look at the definition for the first layer here, in addition to the dimension and the activation function, we're also defining a load factor. Now, this is a knob that allows you to set your computational budget so you can harness the power of deep learning for very cheap, really. In this case, we're using 0.05 or 5% of 10,000. So for each input vector, we're only going to use 500 out of the 10,000 neurons in this first layer. And this is not just any 500 neurons. These are the best 500 neurons that Bolt curates for each sample. Additionally, in addition to training with sparsity, you can also do inference with sparsity. And you can do this just by calling a single method, which is enable sparse inference. So in this case, enable sparse inference is basically enables you to use sparsity also in inference. And the difference is one of the benefits of using Bolt to do sparse inference is, since we're also training with sparsity and the network knows that we're going to use sparsity in inference, it really optimizes for that sparse inference. So you're using the same network for both training and inference, which leads to performance benefits. Now, as you can see, each epoch here took only about 3 seconds to train. So if we think about it, this is a 51 million parameter model, while the MNIST network above is only a 700,000 parameter model, I believe. And that also took about 3 seconds per epoch to run. So here we're seeing, because we're using load factor, we're able to have a model that's about 70 times the size of the model before, but each epoch of training runs in about the same amount of time, which is very exciting to us. And as you can see, after 3 epochs, we were able to get the accuracy up to 83%. So yeah, that's very exciting to us. The fact that we are able to scale the model to 70 times as large and still train in about the same time. And now that we've seen how training time scales with the size of the model, we want to show you how you can use even larger models. So in this case, we're going to pivot to a different task, which is sentiment classification. So in this case, we're going to use the Yelp review dataset. So as the name suggests, these are reviews on Yelp that you would have to classify between a good review or a bad review. If you like the taco place, then that's maybe a positive review. If you don't like, I don't know, whatever other place, then that's you might write a negative review. So as you can see here, to do this task with Bolt, we first vectorize the queries, these sentences, into vectors of 100,000 dimensions, which, if you think about it, is quite big. But that's also one of the benefits of natively supporting sparsity. You can imagine you can have so much flexibility with feature engineering, and now you can extract such a rich feature set from each sample, so that you only need to train on, so that you can have an accurate model after training just on one corpus. Yeah, so we're passing. So this is a 200 million parameter model. We have an input dimension of 100,000 followed by a hidden layer of 2,000. So that's 200 million. And we were able to train this on a CPU for just a few minutes. But it's still a little long for this. Demo. So instead, we're going to take this chance to introduce you to our save feature. So in practice, we're going to want to train a model once and then keep using it for inference So it's really important to have the ability to save a trained model. So we bake that into Bolt. All you have to do to save your model is to call the save method as shown here, and then you pass in the file name that you want to save it to. And then when you want to load it back, you just have to call the load function. So let's load it here. All right, so we successfully loaded the model. Okay, and as a benchmark, we compared it to Roberta, one of the state-of-the-art NLP models. So Roberta is a 300 parameter. It's around 300, has around 300 parameters, and it comes pre-trained because it takes a lot of data and a lot of computing power to train. In fact, this model was trained on 100 gigabytes of data for a total of 1 month on a fleet of 8 GPUs. And so this is not something that any developer can just train on their own. So in fact, instead, what we do is we download a pre-trained model, a model that has been pre-trained on a more general understanding task like masked language modeling, and then we fine-tune it on the data set of our choice for the task of our choice. And this performs great. However, it is known that you can really get even better results if you train from scratch on the task that you actually want to do. So in this case, we ran it on Roberta and we got around 83% accuracy. And we think Bolt can do better. So let's actually run the prediction API and see how well Bolt does. All right, and we just see, as you can see here, we got 93% accuracy, about 10% more than Roberta did. So this is an example of a use case where training from scratch on the task that you want can actually reap really tangible benefits. As I said before, we really like large models here, so we prepared an even larger model, this time a 1 billion parameter model that we trained on a slightly larger text corpus. It's the Amazon Polarity dataset. And this will allow us to do an interactive sentiment analysis demo. Yeah, so in this case, it's a 1 billion parameter model. We trained it on CPU for only an hour. And once it loads, I'm going to type in some sentences and it will tell me what sentiment it thinks it is, whether positive or negative, in real time. So to start off, let's go with something very simple, something that is clearly positive. All right, so it managed to get the right result. And now let's try the opposite. Let's say I hate you. All right, and once again, it was able to predict correctly. Let's give it something a bit more neutral, but also contextual. Something like chocolate. And as you can see, it was able to. So from these three results alone, we can see that it's able to capture the sentiment of simple sentences as well as the context from the training data that it learned from. Now, I want to give it something a bit more complicated, maybe something that has both a positive and negative sentiment in the same sentence, but with an overall negative sentiment, like I like chocolate, but it makes me sick. All right, and as we can see, it also managed to get the right answer for this one because it has an overall negative sentiment. So from here, we can see that it's able to learn to understand even more complex sentences. Now let's get a little bit real for a bit here. I like ThirdAI, but let's say I'd rather work somewhere else. And let's see where this takes us. All right. And of course, I'm just kidding. So, and there you go. And there you have it. With this demo, we were able to really get a feel for how well Bolt is able to predict the sentiment of sentences. It was able to predict it for both simple and more complicated sentences. But that's not it. One last thing, we want to talk about speed. So we talked about, oh, right, I have to stop this one first. So let's stop that one. So we talked about training speed. We talked about how we were able to train a 1 billion parameter model on CPU for just about an hour. So now we want to talk about the inference speed. Once again, we're going to compare it to Roberta, which in this case was able to find the sentiment of the sentence "I love chocolate" within 350 milliseconds. So 350 milliseconds, and Bolt did it in up to 6 milliseconds. So that's about a 50 times improvement in inference time. So just to reiterate, we trained a 1 billion parameter model on CPU. We're getting state-of-the-art accuracy, and we're with an inference speed of up to 50 times as fast. This is very exciting for us here at ThirdAI, and we hope you're just as excited about it. And with that, I conclude this demo about Bolt and pass it over to Josh to talk about a document search with MaxFlash. Thank you so much.
Okay, perfect. So yes, thanks Giordi, thanks Vaidi. That was awesome. Now I'm going to talk about document search, which I think Vaidi alluded to. It's like looking for a needle in a haystack. So what's the problem with document search? What does that really mean? Well, the problem is basically to find the most relevant documents to a query or a question from a very large corpus of documents. So say your corpus is Wikipedia, and the goal is basically to say, okay, given any question that could reasonably be answered by Wikipedia, by any document in Wikipedia or any passage of Wikipedia, find that specific passage and return it to the user. This is actually the backbone of fields as varied as product search, automated customer support, and ed tech. You know, something like product search, you might be searching reviews and wanting to answer questions about wanting to answer questions about a product. Or you might be searching for a product and want to search all the descriptions of different products to find the most relevant products. For automated customer support, a customer might be asking a question and you want to search a very wide bank of frequently asked questions and their responses to give a good answer. And for something like ed tech, you might have a textbook and you want to search, given a question, you want to return the part of the textbook that answers that question. And so you can see that document search is really widely used in computer science. It's a very fundamental problem, basically information retrieval. And most people still use lexical search, things like Apache Lucene or Elasticsearch. And that works, but in the last 10 or so years, people have found that semantic search can perform more than twice as well. But the problem is that semantic search can be very slow on a CPU. So most people still use lexical search because semantic search, is very difficult to put into production, and it can take even a few seconds to do a query. And really, you want to return responses to user queries in less than 100 milliseconds or so, or a couple hundred milliseconds. So enter ThirdAI document search, which is powered by our MaxFlash engine. And so sparsity allows us to avoid billions of vector multiplications that take so long for each query. So we still get very fast speed, like Elasticsearch or lexical search level speed, while still achieving the accuracy, more than 2 times accuracy of lexical methods. So twice, would basically get the speed of lexical methods and the accuracy of semantic methods. Okay, so let's jump into an example here. I'm just going to do some imports, and now I'm going to load an index that's been pre-built with the MS Marco passage ranking data set. So I'll just run this because it takes a minute or so to load it, and then let me explain what MS Marco is and why you should care. So MS Marco is basically a data set that has 8.8 million passages from all across the Bing search engine. So basically, Microsoft curated this data set that has that had the most common that had basically a bunch of different top return passages. And then the goal is basically to say, okay, given a query, find the most relevant passages from that huge index. And this is actually a benchmark for most information retrieval algorithms, and there's a whole leaderboard. So when I say that we achieve state-of-the-art accuracy, that's as compared to all other methods on that leaderboard. And so, here I say we achieve MR at 10, which is, kind of like a recall metric of how often you achieve. It's how often you retrieve the top result in the first 10 of we achieve of 0.38, which is pretty much state of the art. And like I said, this is about twice the lexical method. Lexical methods usually get around 0.17 to 0.2% MRR. Okay, so now let's just run the demo. So here we can see, I just want to say it's very easy. We just deserialize the index from file. We've already pre-saved it. We also loaded an embedding model. And now I'm just going to run a nice little interactive demo so you can see what the demo is doing is we'll read the query, embed it, and then query the index with it. Okay, so let's just ask so MS Marco, like I said, has a bunch of general knowledge passages. So let's just ask some general knowledge questions, like when was flight invented? Okay, and you can see it says we got a pretty good answer. The history of the airplane shows it was invented by Orville and Wilbur Wright. They got the patent 9 months prior to the flight, December 1903. So you can see here that there's no real, like, a lexical method might not, this says the history of the airplane. Something really that directly says, oh, you know, like when was flight invented, all close together, that a lexical method might need. This is very semantic, like this is the meaning. We're going for the meaning. Let's try a different one, like how does a car drive? Here we say the powertrain provides power to the car, power to my engine. So that you see this is, again, exactly how a car drives. And there's nothing here that's really a direct lexical match. We can say, for like, how much is a shipping container? A shipping container you can expect to pay around $3,200 new and between $1,400 to $2,000 used. So you can see, you know, again, there's nothing really here. There's no word much here. It's kind of like you need to know that how much the shipping container is asking for the cost of a shipping container, and then you need to know that this response is talking about how much a shipping container costs. So you see, you need some sort of meaning here. Okay, but you know, what if we want to add something new? If I search what is ThirdAI, you know, it doesn't give us anything about the company because this is a general knowledge data set that was made a few years ago. So let's add something new to our index. Oh, whoops, I also forgot to end this little demo. Let's add something new. We're just going to add the first ThirdAI webinar. And then if we run this again and we say, when was the first ThirdAI webinar, we get this result. So that's great. That's awesome. But what if I want to build an index from scratch? You know, this general knowledge index is not always so useful. So here I'm going to load an index that I've pre-curated data set that consists of all the Wikipedia articles that are about deep learning. And so we have about 800 or 1,000 passages or so that we're going to add to the index, and you'll see it'll take about a minute or so. And yeah, basically the key thing here is that for every document and for every text, we're going to embed it and then add the document. Okay, so this will take a little bit and then we'll query it. And so the idea here is that if you have specific, like domain specific, you know, document search or question answering problems, you can just easily build an index with this Max Flash engine and then query it, achieving state-of-the-art semantic results with a very fast and very quick amount of time. So here we say, okay, well, let's ask some questions like, what is the difference between supervised and unsupervised learning? And also, by the way, it'll catch spelling mistakes because you know, these are embeddings, and it's just spelling mistakes will map to about the same embedding. Okay, so unsupervised learning, no labels are given to the learning algorithm, leaving it all on its own to find structure in the input. Whereas, you know, let's see, and unsupervised methods cannot be used. So, you know, we're getting information about supervised and unsupervised learning here, and there are differences between them. We also might look up, you know, machine learning issues and flaws, right? And we see, although machine learning has informed in some fields, it's often failed to deliver expected results. Reasons are numerous: lack of data, lack of access to data bias, privacy problems. And we also get this interesting about adversarial machine learning, which is ways that when people come up with, you know, bad examples, try to fool machine learning models. We also might look up who are the most important people in machine learning, right? And we see, okay, cool, we get a very interesting list of people that are influential in machine learning. And the key thing here is like this list of people, right, does not obviously have a lexical match. All these things don't have obvious lexical matches to the queries. We're really searching based off of meaning. And with that, that's the end of my demo here.